In the previous unit, we've looked at lots of important fundamentals. We looked at types of forces. Okay, remember there's a whole bunch of forces. And we have looked at torque. What is torque? Rotational stuff. So now we are almost ready to think about what is equilibrium. But before that, hang on a second. We need to know what is a center of gravity. Okay, so in this video, we will look at what is a center of gravity, because this is a very important idea for equilibrium. First question, what are these dots? Okay, so recall a little bit, we looked at it in the previous chapter 4, where we look at skydiving. Okay, when we have a person falling from the sky, some forces act on this person, and we often draw this diagram. A dot, an upwards drag force, I'll say this is drag, and some downwards gravitational force, which is pulling this man down to earth. Gravity. I'll just write gravity. Lazy to write the whole thing. So the question is, what are those dots? In this case, what is this dot right here? Is that the man's head? Is that a man's knee? Is it the body, the hand? How do you know which part of it? That's the question we want to answer today. That dot, we can say, in simple terms, is some point on this man's body, maybe here, perhaps. And we say, we'll use that point to represent the whole man and then draw forces from there. So we have FG and then we have FD. Okay, so the basic idea is, in plain English, the dot is some point on the man's body, but there's a proper term for it. Let's take a look. Ooh, this looks familiar. Here's another example before we look at the proper terminology for this kind of stuff. This is a familiar projectile we looked at. Make sure to review this for your coming tests and make sure you don't forget everything, okay? So projectile motion is in this shape. We often talk about launching a ball, what's it called? Bowling ball, tennis ball, something's launching. But what if this dots that we always use to represent is not a tennis ball or basketball? What if it's something else? What if it's a ninja shuriken, flying and spinning at the same time while in projectile motion? Oh, what does the dot represent then? So here we have a ninja knife, I don't know what you call it in English, ninja blade spinning while it is traveling in the projectile motion. The dot that we would use for this ninja blade on the right, we would probably choose, what shall we choose? Would it be the dot on the end? Either end? Most likely you would choose the dot to be the middle piece right there. So that middle piece will be what's following this whole projectile path that we have looked at a lot. To illustrate that a little further, if you've seen people do all these fancy flips and spins on their snowboards and skis, you will see some pattern like this. Whew! Hey, that's a projectile. But notice how the person's legs and arms and heads are all over. If you track this dot that we're talking about, that dot would follow the path of a projectile, like how we usually draw it. Wow, I can't really see the dot, right? Now I'm trying to make it bigger a little bit. I'm trying to draw dots. Anyway, so there's a dot there, and we are trying to figure out what that dot has to do with everything else. Now let's take a final look. Same picture, but two of the same kind together. Notice these two. What's the difference between this diver jumping off the diving board? On the left side, the fellow is just straight up, boing, jumps in. On the right side, this person, boing, but does some fancy spin, like what we talk about. One is what we say only has translational motion, means up, down, left, right. That's it. The person is moving up, down, left, right. But on the right side, this person is going translation and rotation at the same time. So translation means the dot is moving, I would say, but the person's hands and legs are also turning. Looks like it's turning this way, turning that way, turning that way. So this kind of brings a little bit the idea of torque into the system. But the most important thing I want you to remember is this. You look at that dot we've been talking about. No matter what rotation it is, this dot is still the same nice projectile path. That dot, now we have a name for it. It's called the center of gravity. So all objects have center of gravity. We humans have center of gravity. In this picture, this lady's center of gravity is somewhere near her stomach, her hips. If you look back at this good old ring, the center of gravity is probably right in the middle of the ring. So if you throw it like a frisbee, it's going to spin about the center very nicely. Anyway, so all objects have center of gravity, and there's a definition you should know for A levels. So for the center of gravity, we often use the shortcut name CG because we are lazy to say the whole thing. So if you see the word CG, it means center of gravity. At A levels, you want to remember the definition, which goes like this. Center of gravity is the point, remember we talked about the dot, the point where all the weight of the object can be considered to act. So, for example, if you drew those earlier things like, you know, the dot, and we say, oh, this is the weight acting on this object. That dot is basically the center of gravity, and that's what the whole sentence means. So remember this picture we looked at earlier from a previous video or the one before that? This is a picture of a dancer doing a freeze, like a pose halfway during dancing. Take a guess where the center of gravity for this guy would be. Where would it be? Here's some tips. I wouldn't say the center of gravity is at his knee. It seems kind of strange. Because center of gravity is the distribution of weight. Most of his weight is not exactly at the knee. And if you think about it, if I choose the knee as the center of gravity, then if I find the torque this way and this way, the clockwise torque is going to be much more. The head, the body, the hands, so no. I don't think the center of gravity is over there. Where it likely is right here. I'm making a guess. An educated guess, by the way, not simply guess one. So why I guess there is, firstly, for humans, your center of gravity is roughly near your stomach, around your stomach area. Depends, different shape, different weight distribution. But generally, for guys, it's somewhere in the stomach, maybe a little higher because a lot of guys' weight is in the upper body, okay, the shoulders, the chest, and the arms. And for ladies, it's a little lower in the stomach area because a lot of the ladies' weight is distributed more towards the lower half of the body. So in the thighs, the legs, the hips, and so on. Okay, so for this guy, probably somewhere here. And if I draw an arrow, weight is going to be like that. So the weight of this guy can be considered to act at that point, that one point. Because, and if you check, well, you check the torque this way and the total torque of all the weights here, because you know the ear has a weight, the head has a weight, the neck has a weight, the legs has some weight. If you draw all the weights, they all balance out nicely, then that is the center of gravity. The last reason why I chose there, kind of a sneak peek of the equilibrium chapter, equilibrium section coming next is notice how this weight line, this line of action goes all the way down. You can't see the hand, but the hand is somewhere from here to here. This line of action of this weight is within the base support. So if he's stable, means he won't fall down because his center of gravity is within the base support where you have some, I don't know, a few maybe normal reaction force to support that weight. The same idea goes for other dancers as well. If you do dancing or you do sports, a lot of what dancing is the dancer is very aware of their center of gravity. Okay, they may not know it, but their body knows it. Like I said, your body actually knows more physics than you by experience. You just need to learn how to calculate it. You're already living physics. So if you look around, all these dancers, they all have their center of gravity. The one on the left, on tiptoes. I'm guessing the center of gravity is somewhere along this line, because if I say she's equilibrium, she's steady. Probably her center of gravity is there. There. Okay. And you can say the weight is set to act on that point. For this lady, the bottom left is a little in the curve shape. So probably the center of gravity is somewhere actually outside her body. So somewhere like that. That is the center of gravity. It can be outside the body because it's a curve shape. Okay, so somewhere here, again, partially because if she's balanced, uh-oh, I missed her toe, but she's supported by a toe, so somehow the center of gravity has to be in the same line as the support base of the toe so that she can actually do that pose and not like immediately fall down because of the torque. Because if the center of gravity is away from the base, then oh, we're gonna have some torque there. Anyway, same thing for this guy in the middle. I don't think he's balanced. I think he's gonna fall down actually. So he might fall down this way because it looks like his center of gravity is somewhere here. And it's kind of hard to see because it's a 3D picture and 2D image. But if his weight is a little down and his support base of his hand is down here, ooh, looks like it's going to be a torque. This weight is going to cause him to fall down this way. Lady on the right, nice poses. Normally, the center of gravity would be here, but because of how she has distributed her arms and legs, you can see the center of gravity, the weight distribution, it's kind of probably a little on this side, a little on the side. And you can double check. Ooh, she can probably balance too because, wow, at the tip of her toes, because the center of gravity line of action is somewhere near the base. So we'll look more on equilibrium versus not equilibrium in the final chapter, but for now, we're going to focus on center of gravity. Now, how do you find the center of gravity? We look at some ideas, looking at the base. But if you have an object, like let's say a knife. Okay, here's a knife. It's a little blade. If I want to find the center of gravity, I have to just do a little seesaw thing and try to balance it on my finger. I'm trying. Patient. There we go. So once I balance it, I have found the center of gravity, which is right there. Okay? Notice how it's not exactly in the middle. Okay, this side is a little heavier, it's short. This side is longer, but it's lighter. So now I found the center of gravity. Now what? Now what if I open the blade? So I open it. Now it's much longer. If I try to use that same center of gravity to balance it, uh-oh, it's not going to balance. It keeps wanting to tilt down. So from my original, I probably have to move up the blade a little bit. Okay, to account for this whole extra weight distribution. So let's try moving up a little bit. Ugh. Nope. Balance. Nope. There we go. Oh, perfectly balanced. Kind of. So now there's a new center of gravity. Ooh. The weight is the same, but the distribution, because I opened this part of the blade up, the distribution is different. So now you have a different center of gravity. So yeah, one way to find object is balance it using torque. Okay, so once it's balanced means the torque on this side, because of all the weight is balanced with the weight on this side. Weight. Oh my goodness, I'm scared to drop this because then it will stab my computer down there. Okay, so just remember, center of gravity depends on distribution of weight. Distribution is important. Let's look at a past year question to see how we can do that. First one is a ruler pulley. No, why did I say ruler pulley? That's not a pulley. My apologies. Just a ruler. There we go. This is on page 11. If you have the handout and want to try it out as well, you can pause the video and do it ahead of me. But the question goes like this. You have a ruler pivoted with that triangle thing. A 4 Newton weight is suspended, causing it to rotate. At the instant when it's horizontal, what is the resultant turning moment about the pivot? So you have the ruler that will start to rotate, but the moment when it's horizontal, they're asking you what is the turning moment. Torque. So let's look at the diagram first. One important thing I want you to highlight is the word uniform. Uniform meter rule. It basically means the mass is evenly distributed throughout the whole ruler. Okay, it's not like the humans we looked at before. Like if you lie flat on your bed, your head's much heavier than your legs. So depending on where you are, the mass is not evenly distributed. But for rulers, yes, you can assume, especially when they say uniform meter ruler. So if your ruler is 10 cm, 5 cm in the middle is the center of gravity. Okay, so this one, what's going to cause this ruler to turn? Oh, we have a weight hanging there. That weight's going to cause a clockwise torque. That's it. The resultant turning moment. Wait a second. We have weight of the ruler from the center of mass. But where's the center of mass? Uniform. So you need to remember that. So if this is a 100 cm ruler, the center of mass will be acting at the 50 cm mark. This is kind of like the lab you all did a couple weeks ago, where you're trying to balance the ruler about a triangle wedge. Let's see, how heavy is this thing? The weight is 2 Newton. Okay, so the weight's going to cause an anti-clockwise torque. You want to cause the ruler to turn this way, rotate about the pivot, and you want to find a resultant. Nice. So resultant, this funny sigma symbol is Greek for resultant or net. The sum of all the torques is, you need to choose a direction, friends. Let's say clockwise is positive, anti-clockwise is negative torque. Because direction matters, okay? So, we have, let's do with the clockwise first. 4 newtons times, how far away is that weight from the pivot? Don't say 60, 60 is the, from 0 to 60, no. We only want from 60 to 100, that's the distance. So we do 4 times 40 cm, which is 0.4 meters. Minus, well, plus minus, the other side, so the center of gravity, let's label it COG or CG. Nah, never mind, I wrote the O already. Center of gravity. That one will be 2 newtons times, not 50 again, this distance between 50 and 60, so that's 10 cm, so 0.1 meters. What do we get here? Resultant torque. 4 times 0.4 minus 2 times 0.1. So we get 1.4 Newton meters for this case. Okay, a quick refresher or reminder is, this is clockwise torque. This is the anti-clockwise torque. If you define your signs differently, like your positive and negative are different, you will still get 1.4 just with a negative, which will tell you which direction it is. So for me, I said clockwise is positive. So this positive 1.5 basically means clockwise. It's going to have a net torque that is clockwise. So in the end, the whole ruler will still swing down. So that's the ruler question. Now we look at the van question. What if it's something more complicated? This one, the question is, you have a stationary van. Stationary? Remember the word stationary? Just now we said the ruler is moving, so there is a net torque. Now the van is not, thankfully the van is not rotating, so it's stationary. Let me highlight that for you. What is the horizontal distance of the van's center of gravity? So we're trying to find where is the center of gravity from the front of the van. So from the front, where is the center of gravity? Somewhere here? I'm guessing it's somewhere there. We don't know for sure. Wait. But where is it? Pause the video, try this out, and then come back and we'll take a look how you can solve or find where the center of gravity is. So, first things first, if you feel a bit confused, like, oh my goodness, this is not a rod. Miss, why suddenly got a van on? How to think about it? You could model this van as a rod. My lines are not straight. So this rod has the weight somewhere near the middle, maybe somewhere at the side, I don't know. Weight. And then you have the normal forces at the tire, 9,000, 16,000 Newton. Well, we need to think of torques, like we mentioned earlier. But talk about what? Where's the pivot? You choose the pivot. Okay? You can choose the pivot anywhere along the whole rod. But for convenience sake, I'm going to choose the pivot at the front of the van. Why is that? If I choose this as my pivot, then I'm solving torques about that pivot, which means later I can just find the distance between the center of gravity and the pivot, which is what I'm trying to looking for. Okay, we're trying to find the center of gravity from the front of the van. So choosing the pivot at the tip is convenient. You can choose it elsewhere and solve it. You just have to do extra work at the end. Okay, wow, where is my cursor? There it is, weight. So the weight is the center of gravity that we're trying to find. Let's try it out. So stationary means no net torque, thankfully. Otherwise you'll be like those mud rapids, those bikers, they pull up the front wheel and then they drive. So no net torque. Okay, so we do the same thing. We have clockwise torque plus the anti-clockwise torque. You need to choose which one is negative, which one is positive. So weight is going to cause a clockwise torque. Oh, I shouldn't write it like that. After you think it's an extra force. Weight is going to cause a clockwise torque, and all the normal force will cause an anti-clockwise torque. Let's say this is positive, these are negative. So clockwise torque, we have the weight of the van. Do we know the weight of the van? We don't. Can we find it? Yes, I think we can. We have to use the idea of no net force. What does no net force mean? Your van is not floating in the air. It's not sinking through the ground. So it means somehow your weight is balanced with your two normal reaction forces, R1, R2. Well, I didn't draw the arrows to scale. Sorry about that. If R1 and R2 is that long, then your weight should be doubly as long. Okay, so your weight, yes, you can find it. Weight is actually, yes, right here. Weight is 16,000 plus 9,000 Newton. Because the up equals down. Because your van is stationary and not floating or sinking. So let me do a quick calculation. 16,000 plus 9,000. 25 kilonewton. Woo! We got the weight. Whew, scare you for a moment. Scare me. Okay. So 25000 times. What's the distance? We don't know. We're trying to find that. Okay. D. Plus. Or I say the other ones are going to be minus. So minus 16,000 times, let's put the times in the bracket. How far is that 16,000 reaction force from the front of the van? 0.6 meters. Okay. Minus the other thing that's going to push it clockwise is the 9,000 Newton reaction force. How far is it away? 15 plus. So, sorry, 1.5 meter plus 0.6 meter. So that's 2.1 meters. Equals to 0. By the way, if you rearrange this whole equation, you're going to get something like clockwise torque equals to anti-clockwise. Wait a second. Clockwise torque equals to anti-clockwise. That's correct. Torque. That's basically, you can rearrange it to that. It's a shortcut if you want to skip the first few steps here. But I write it out all for you to see so you can make sure. Okay, so you rearrange, find D. Okay, let's go. So 16,000 times 0.6, 9,000 times 2.1, divide by 25,000, 1.14. So then you can say that, this weight force, which is the center of gravity of the van, has to be 1.14 meters away from the front of the van. And that's how you can find the center of gravity for this van. The final one is the footbridge. What is the footbridge? Let's take a look. A uniform horizontal footbridge. Oh, the long thing that the man is standing on. That's a footbridge. 12 meters long and weighs 4,000 Newton. It's resting on two supports. Okay. Man standing on it. And they're asking us, what is the upwards force from support X? So they're asking, what is this force? You know, what force is that? That would be a normal reaction force. And we're trying to find what that is. By the way, there are two. There's one here, one from the other side as well. Just FYI. Okay, first step when you see questions like this, draw all the forces at play. Anything you know from your types of forces, reaction, friction, well, nothing's moving, so no friction. Also, remember the keyword, uniform horizontal footbridge. What does it mean, uniform? It means the weight is evenly distributed throughout the whole rod. So, we have the man's weight, right? Let's draw that out. So the man has some weight. Did they tell us how heavy he is? Yes, they did. 600. Let's just draw it out. So 600 is the man's weight. And you have the footbridge center of gravity. Now, you know it's horizontal, so it has to be dead in the middle. 4,000 Newton. So if the whole footbridge is 12 meters, means this will be 6 meters, and the other side 6 meters. I'm not going to label it. Okay, so we got the forces. Double check. Yes. Now, the next part is, you need to choose a pivot. Where are we going to choose it? You can choose it any point along the entire line, but where you choose it will either make your job easier or make your job harder. See, we could actually choose the pivot to be at support X. There's just one problem there. We are trying to find the force at X. But if you choose the pivot at X, R1 has no effect on the whole system. So we don't have an equation with R1 inside. That's a problem. And we will find support Y, R2 instead. And you have to use some other method using equilibrium. All the upwards equals to downwards to find support X. That's a longer method. So let's choose a pivot somewhere else. Let's choose it at Y. By choosing at Y, I can have an equation of torque with R1 inside. And I also kind of get rid of R2 because R2 is exactly at the pivot. So force acting on the pivot is pretty much no effect. Why no effect? Because torque is force times distance. Distance is 0 already, so torque is 0. So all the forces that act here, if there's a whole bunch of them, all don't matter anymore. Great, I like it. Simplify a bit. Now, what should we do? Is the system turning? Is it at rest? Net torque. Next step is think about the net torque. It's at rest. Keyword is in the question. So if you write it out, net torque is 0. Which means you can say that clockwise torque is the same as anti-clockwise torque. Wait. If you're asking where's the negative sign means, go to the previous question and check. I kind of skipped that step, showing the negative sign, because I want to jump straight to this one for net torque 0. So, clockwise forces, what are those? We have 600 times, oh, we don't know that distance. We can find it though. Whole bridge is 12 minus 6 minus 4, so this should be 2 meters. So 600 times 2 plus, clockwise, anti-clockwise. I forgot, my pivot's on this side. So the torque, these fellas cause an anti-clockwise torque, and R1 is causing a clockwise torque. Ha! Got it reversed. So clockwise torque should be R at X. Let me just change that. Rx times the whole length, 12. Only one force. Wow, okay. One force to support everything. Good. Then the anti-clockwise. Now only correct. 600 times 2 plus 4,000. No, not times 2. Wow, why today the question? Okay, 8. That's right. 600 to the pivot is 8 plus 4,000. How far away is 4,000 from the pivot? 6 meters. So you 6 meters. Now we have an equation of torque where you can find your support at X, which we call Rx in this case, reaction force at X. So calculate. What's the reaction force at X? We have 6,000 times, 600 times 8 plus 4,000 times 6 divided by 12. 2,400 newtons. This is the force, by the way. So the answer is, for this whole thing to be at for this whole uniform rod to be at rest, support X should have an upwards reaction force of 2,400 to support everything. The man's weight and the weight of the footbridge. So remember, just recap a bit. Whenever you see all kinds of torque related problems, first thing is, if there's a picture, label your forces. If there's no picture, you need to draw your own diagram. So you need to draw a diagram. Okay? For dynamics and mechanics, if no diagram is provided, please draw a diagram, even if it's just a simple rod. So once you've labeled it, then you need to check which one is clockwise torque, which is anti-clockwise. You need to define your directions. Okay? Which one's positive, which one's negative, where and what. Then you put all together. Also, I should mention net torque. You should check the question. Is it net torque 0 or otherwise? Then lastly, of course, you can solve. So just remember, the main problem solving framework is break down each situation force by force and think about the torque. So that's all for this section on center of gravity. Don't forget, objects have center of gravity.